We can continue the discussion and.
A good question.
I think there isn't a definite range, but there should be a difference.
Because we need to identify that.
You continue answering.
If you want to say someone is healthy, you need to know what is the healthy range for them.
Yeah, there are some areas in this overlap, so you cannot, it's classification. So probably you cannot have a definite range. You just have a trending saying that. Okay.
Thank you so much. Is this yours? Zhuo, did you want? Okay. Thank you, Professor.
Okay, good job. So I'll talk about you can see that physiologic signal processing and linked to humans, including values there's scattering inside the human tissue. These are complex systems. So when you want to do good, interesting research, for the human
You can get more grants.
So do automatic control, when I was an undergraduate student learning automation, I feel like humans should kick out of the loop. So right now you can see we're bringing human into the loop again. That's the new trend. So human-centric. Human-centric automatic control. Okay? So the building. The ultimate goal is to make the building automation, to make humans oxygen. How can you tell they are competent? Now, you can use a cell phone control.
Yeah, I'm ready.
Okay, Zhuo's topic is very important as well, and we can learn why. Go ahead.
Yeah, thank you, Dr. Chen, for your introduction. So my name is Zhuo Li, and I'm Dr. Chen's student. And my topic is on the chamber plasma DC bias induced by the forced superdiffusion. So with a subtitle of anomalous diffusion. So we usually say, besides the standard diffusion, there are anomalous diffusions. So either even more anomalous on the anomaly on the anomalous diffusion. So I'm trying to explore that. By the way, thank you for this. My outline is covers the motivation, objectives, introduction, and some preliminary simulation results, although with the literature, conclusion, and references. I'm sorry, I have just to go for this. Oops. Yeah, so my motivation is, the motivation for me to choose this topic is because my research emphasis. Oh, thank you. Research. Yeah, I can live with this.
You can use this one point.
Oh, thank you. Thank you very much. I'm working on a project, joint project with with a wafer processing company in the industry, which between the MISA lab and the lab research. So my major focus is on process controls. So this is my side interest, some of my side work. So when I learned the fractional calculus, I'm motivated to spend some efforts on this side interest because they come up with some questions of the estimation of the DC estimation anomaly of the DC bias voltage on the plasma chamber. And so how is it estimated? It's by some virtual metrology during the real processing. During the experiments or laboratory testing, they can accurately measure that value through some plasma physics technologies. However, during the real industrial run, those those approaches are too invasive, because as long as the probes are inside the chamber, they affect the plasma. So what they measured is not the real value we see, and it affects the uniformity of the process, the wafer processing process. That's why they cannot really use these tools during the in practice. So why? In our class, when I saw these slides, then I was motivated to do some research on characterizing the potential reasons for the estimation anomaly of that DC bias. So my objective is to identify the relationship between the micro-level diffusion characteristics with the micro-level physically measurable quantities, as what Einstein did. So of course, I'm hoping. Whether or not I can do that, we'll see. And also to explore the potential cause of the measurement anomaly. So first of all, here's some introduction, background. So what is plasma process? It includes the etching, vapor decomposition, and plasma cleaning, meaning using plasma to clean some transistors on the already etched wafers. So here are some micro-level view of the products, and majorly the principle behind that majorly are using the bombardment and the sputtering of the molecules. And so we saw that it mentioned there are super diffusion in the turbulent plasma. So what is turbulent plasma? So I roughly searched it. I found that turbulent plasma majorly exists in the astronomical point of view, the field, research field. So for the chamber plasma, not many people claim there are a lot of turbulences, eddies, or some extreme cases. However, since it is due to there are very few people doing research on this, then I think it gave me more motivation. So next is about some introduction on the use of this research. So the value of this research can be revealed in the calibration of the equipment variation. So when in the industry, when they build up a plasma etching, plasma processing tool, I mean the chambers with all the peripheral equipments, there are always mechanical mismatch, mechanical uncertainties, which resulted in the equipment uncertainty, equipment variation. So when they run the same recipe on one tool, the recipe means temperature, gas flow, all the control the variables on that tool. When they run the same recipe, they will get different results. So this research can contribute partially to these efforts, and also to the plasma diagnosis. So here are some literatures. I'm not going through in detail. So before we go into to discuss about the plasma DC bias, it is the principle of how the plasma is formed. There are a lot of formation measure approaches for the plasma. So in the industry, most of what they use is so-called the glow discharge by the RF power. We can use DC as well, and in the universe there are a lot of plasmas generated by all different means, all type of approaches. However, here we are talking about this RF generator. Okay, I used the wrong figure. I'm talking about RF generator induced ignited plasma. So here is talking about the Townsend avalanche effect. And here is some background of the formation of the plasma. And here is what I'm talking about, the DC bias voltage. So when we form the plasma using two electrodes, one electrode is grounded. And when the molecules in the gas are ionized, they get absorbed in one electrode, and some of the radical, the electrons are propulsed to the other electrodes, so that they form a DC bias voltage between the sheath and the bulk plasma. So I checked the literature that some people are investigating on these topics by looking at the iron energy distribution, electron energy distributions, and also the electron distributions, and also the electron velocity distributions by using the Maxwell-Boltzmann distribution. So I checked those. At this moment, it's very hard for me to fully understand, and it's very not constructive to relate what they are talking about with the measurable physical quantities. For example, what we can measure is the RF power, is the plasma DC bias, and the pressure. The pressure can indicate the densities of the gases, of the gas. However, these models just talk about the micro level distribution, molecular particle distributions. So that's why I set up my objective to be find the relationship between the micro level and the macro level. For now, I still haven't get clear picture. However, I tried to produce some numerical results in some of the papers. So this one is from Lieberman's paper. He's very expertise in this area, and they claim that the magnitude. They claim that the iron energy distribution is alpha to be a transfer function form in the Fourier transform, and it is the magnitude of the filter and versus the frequency. That's what in their paper. So I try to adjust the p and the pi settings, and got similar figures. And here I'm trying to simulate from the basic Brownian motion. So there are hundreds types of code available online that you can download to generate the Brownian motion. As a practice, I quickly sketched my own code, so with a comparison of the Wikipedia figure. So this is just some practice. And here is the standard diffusion. And so this side you can also download from some online toolboxes from MATLAB file exchange. So here I'm just I use 40,000 particles, and each particle has their own attributes and properties. So currently they are running in the centralized algorithm. I'm trying to build a class and object-oriented programming to simulate more particles. So here is for each particle they are doing Brownian motion, so that it can simulate the standard diffusion process. So by by actually doing this, through these practices, I found some detailed problems like that I didn't notice before. For example, when we're talking about the Brownian motion, the waiting time subject to the normal distribution. However, the waiting time cannot be negative. So how can it subject to a normal distribution? And also the normal distribution has a mean and variance. So how do we choose the mean and variance? I think actually Einstein already answered that question because he related that D, the diffusion coefficient, with the measurable physical quantities. However, here we have nothing to measure. I don't have I don't have equipment available right now, so I just arbitrarily choose some parameters for this simulation. So here are some guidance for my next simulation, which is the plasma diffusion. In the paper, there are some guys from National Laboratory, Oak Ridge National Laboratory. So they characterize some characteristics of the plasma. So I followed that, and also downloaded from some available toolboxes for random, all kinds of random, stable, alpha stable, Pareto random, all kinds of random. I tried to simulate, and we can recall Lab 5, simulate the Levy flies. I remember by the time around 2 seconds, there will be a long jump, kind of that. So the long jump is the major differences between the Levy flies and the integer or the Brownian motion, which is indicate of the parallel decay of the probability density function. So here is the super diffusion simulated by this parameter set, probability density settings. So it's a little different. It's hard to say by bare eyes. I need to check the metric to measure this. But here is just a visual, quickly visible view. So for our application, we are talking about the chamber plasma and with electrodes. So there are electric field and magnetic, and in some cases the tools using the inductively coupled plasma, which involve the magnetic fields. So I'm trying to simulate the electric field only diffusion. So by just applying a weak electric field, so they can separate some of the ions and electrons, and so there is one more constraint. So this is the guidance for my next simulation. So as we know that inside the chamber, when we do etching, when we do plasma processing, there are reactions as well, because chemical reactions, they react with other moleculars or radicals or whatever particles. Then they get an annihilation-like behavior. Annihilation-like behavior. That means the ions, the charged particles become neutral. They do not carry charge anymore. So they are not affected by this electrical field. They just randomly diffuse inside this range and collides with other particles. So here is so by simulating this, what I'm using is whenever they absorb to the electrical, they just partially release some of the particles and make them go away. So here is I'm trying to simulate the reaction, the diffusion with force, reaction, and a source. Because in our tools we have a shower header like the gas flow or mass flow controller to inject the gases to be discharged, to be ionized. So I keep feed particles there. So this is how it looks visually. So by going through these practices, I'm getting a clearer logic that whether there is measurement anomaly, there is always anomalous diffusion, so we cannot claim that the measurement anomaly is caused by the anomalous diffusion. But it may be caused by some anomalous diffusion. That means there must be something happen, something triggered that event. So some charges in the plasma, some changes in the plasma are not observed by the regular ordinary measurement approaches, but they do exist and they affect the plasma. So what is it? I don't know yet. And in the industry, I know that there is no answer yet. So my hypothesis is that for the diffusion process inside the plasma chamber, the time scale, the order for the time and for the space scale may vary. They may vary with time, space, or anything else, which is there is no answer yet. So I proposed this one. When the time I proposed this, I thought I found I discovered a new continent. And then it didn't take me long to realize that there are already a lot of pioneers doing this. And Mr. Jianxiong showed me several papers, and now I even realized that in our lab there is a poster by Dr. Chen's student, talking about the variable order diffusion equations. And some people also did pioneer work on this. So here are more literatures for thermodynamics, and a lot of them also contributed to the diffusion analysis. And some books very informative. I have some copies of them, and others I'm trying to collect. And my conclusion is that the current status on this topic is it's an open question, and it's even not widely studied because this is a question posed in the industry. By looking at the literature, by reading the papers, you will see a lot of people are talking about space plasma or whatever plasma. They're just trying to come up with mathematical models. They don't have data support the background. Here in this paper, their analysis does not have data support. So that's the current status. And the evidence are listed here. So my take-home message is, is it possible, or is this meaningful, anomalous diffusion? That means the variable order diffusion equation, can we find physical support behind that? So there are some related topics here. And my future work, ideally, I'm trying to acquire some laboratory data and build a very comprehensive model to simulate plasma diffusion, which includes force, collision, reaction source, and varying diffusion coefficient with respect to time, space, temperature, pressure, R power, and so forth. So here are my references. And thanks to Dr. Chen and Jianxiong. Questions?
Yeah, good timing. Thank you.
Thank you.
So I think we can still spend 2-3 minutes here. So this is a project very interesting. There was a figure, can you do that?
Which one?
You can show this fractional
This one?
frequency response.
Fractional frequency response.
Yeah, you replot it and you duplicate that.
This
yeah,
one. This one. Yeah.
So I want to draw your attention to the expression. The S, the F is like a S, okay, transfer function. So it's like 1 over tau S to the power of P plus 1 bracket to the power of 1 over P.
It's in Fourier. they claim it's in Fourier
It's
transform.
okay.
It's,
But
yeah,
there's
it's
a
same.
corresponding Laplace transfer function. There is a corresponding.
Yeah.
And there's also a corresponding interpretation from impedance point of view. Okay? Like Professor Richard Megan explained impedance. So those are typical fractional order transfer function.
For the ion energy distribution.
Ion energy distribution. So now, if I ask you how you can get impulse response, if I give a time domain signal impulse, what is the output? So that output is called impulse response. And previously you have no clue, but to you now is a piece of cake, NRLP, right? Input is 1 times this. So then you can do numeric things like discretizing, a lot of things you can do. So there's no roadblock for you to do the computation from that. Okay? So Zhuo's summary is very useful, and we are trying to bring this to the attention of the land researchers. Plasma is a rich field of using fractional patterns. I'm convinced. Do you have any questions to check with Zhuo? So, great. This is a very good start today, and I would love to see 3 more presentations if there's none missing. And we're recording this, so we're going to post online. And please polish your slides. Polish your slides and write down your final report and put it into the props. So based on that, I will decide whether you get an A or A minus.
There's no A plus?
Or A plus. Thank you, and enjoy. I enjoy it thoroughly. Okay. Prepare well, and we'll be documented. Maybe one day we'll put on YouTube. Maybe one day. So why? You scared of people steal your publish your ideas? Or?
Yeah.